beliau atau tertarik untuk melakukan penelitian atau membutuhkan kepakaran beliau, maka Anda bukan lagi orang asing bagi beliau, karena Anda tinggal mengatakan bahwa Anda pernah mengikuti kuliah beliau, Anda berasal dari Brawijaya, dan seterusnya ya. Jadi ini saya pikir kesempatan yang berharga untuk Anda untuk berinteraksi dengan beliau. Jadi insya Allah nanti di masa depan itu akan menjadi hal yang berharga ya untuk Anda juga. Selain dari tentu saja selain dari materi yang disampaikan oleh beliau. Nah, bagi Anda yang sekarang tengah mengambil kuliah termodinamika dan kesetimbangan ya. Jadi materi yang beliau sampaikan hari ini itu adalah mengenai apa ya istilahnya, teori ya, teori prinsip, teori fundamental mengenai termodinamika kimia. Jadi banyak sekali akan beririsan dengan materi yang telah Anda pelajari. Nah, mudah-mudahan itu akan mudah-mudahan masuk tambahan dari beliau itu akan memperkaya materi yang telah Anda dapatkan selama ini. Oke, Profesor Matsuhayashi, I'm sorry that I took longer in Indonesian language. Okay, so I think we can start now. So the time is yours.
Okay, so thank you for the introduction. And my name is Nobuyuki Matsuhayashi. And I'm as introduced by Dr. Lukman Hakim. I'm working in Osaka University. And Dr. Lukman Hakim-san was also in Osaka University for 2 years till this March. And we are working together for theoretical analysis of battery electrolytes. And it's a pleasure to give lectures here. And it's a bit pity that I cannot go to the lecture on face-to-face basis, but it's still fine. It's still fun to give a lecture online. And if you think I become very fast in talking, please just let me know. I will slow down. Okay, so as introduced by Dr. Lukman Hakim, the subject of the lecture is chemical thermodynamics of molecular aggregates. And today, which is October 1st, I will talk on quite basic ones. So some of the materials should be already known to you. So it's a kind of relearning the stuff you already know. And the second lecture on October 22nd, I'll go to more application-oriented stuff. It's not really application, but application-oriented. So okay, so I will give a lecture. And our research group, I first want to introduce myself about some about our research. My research group is focusing on soft molecular aggregates, which actually means solution was supercritical fluid, ionic liquid, which is a liquid which consists of only of ions, cation and anions, and their interfaces. And in water, we may also have some self-organizing systems like micelle, lipid membrane. Also, we may have functional molecules like protein in water, and also polymer. These are important functional molecules too. And our focus is somewhere in between molecule and continuums. What I mean is, if you learn quantum chemistry, you focus on a single molecules very, very closely, quantum chemistry is, you know this, right? Schrödinger equation. And on the other hand, this is a world of fluid mechanics. For example, in this case, one usually treats water or any fluid as continuum. So one skips the concept of molecules. Everything is quite continuous. And our focus is in between this quantum chemistry extreme and the fluid mechanics extreme. We treat molecules, but not a single one. There are many, many in the systems. But we treat molecules as a collection of particles, not continuum. So this is our focus. And among molecular aggregates, we focus on soft ones, like myself, or all of them. In all of those aggregates, their functions are governed by order and fluctuations at molecular to micrometer scales. For example, myself. When you write micelles, you may usually write something like something spherical stuff like this. But micelle is roughly spherical, but it's not exactly spherical. It is always fluctuating. Structure is always fluctuating, and due to the fluctuations, structure is different from exact sphere. So fluctuation often matters in soft molecular aggregates. And for example, for polymers or solutions, even in those cases, there are not distinct, well-ordered structures in them, but they still have functions. How they come from, that's our questions. So by focusing on soft molecular aggregates, our research group is try to reveal the functions coming from the formation of aggregates from molecules. And when we say functions, this is a kind of abstract expression. So we want to be more specific. And to specific, functions of molecular aggregates means partitioning and transport. Partitioning means dissolution or molecular recognition or absorption and adsorptions, and they are usually quantified by free energy. Transport means electric conduction, diffusion, viscosity, or heat conduction. They are usually quantified by transport coefficient, like electric conductivity, on which Dr. Lukman Hakim was working, or diffusion coefficient, or viscosity, or thermal conductivities. And both of them are actually functions of one, intermolecular interactions, two, mode of aggregations. What I mean by mode of aggregation is, roughly speaking, shape of the system. For example, micelle is, when you say micelle, you typically think about spherical micelle. But sometimes micelle can be cylindrical. So this has a different shape. And in a more general term, we say mode of aggregation is different. So this mode of aggregation is quite important to see the functions of molecular aggregates. Even from the same molecules, if mode of aggregation is different, the functions of partitioning or transport can be quite different. So we want to seek for unified principle, and to find the unified principle, we especially focus on solvation as a framework to analyze the partitioning as a kind of unified principle. So this is a subject of my talk in October 27th. So our research group is actually many of our research groups are working on MD simulation and statistical mechanical theory observations. Okay, now let's move on to the contents of this lecture. So here we are focusing on chemical thermodynamics. So thermodynamics. And thermodynamics is often taught as part of physical chemistry. Then what is it? You know it. Inorganic chemistry deal with inorganic compounds. Organic chemistry deal with organic compounds. Biochemistry deal with bio-related molecules. So compounds, molecules, or compounds, and so forth. Then what does physical chemistry do? Many of the focus of physical chemistry is collection or aggregates of molecules or atoms. If one focuses on collection of atoms, that provides, goes to, one has to deal with chemical bond. And if one wants to know deeply about chemical bond, one has to study quantum chemistry. This is the reason why quantum chemistry is very much taught in the classes of chemistry. And if one focuses on the collection or aggregates of molecules, that comes to thermodynamics. And if you go to the microscopic level, one needs statistical mechanics. And today's lecture is focusing on thermodynamics. And then why physical chemistry need to be learned? Because real problems are very often a problem of molecules and their aggregates. And so to treat molecular aggregates, physical chemistry is necessary. Therefore, physical chemistry or thermodynamics is actually a quite necessary and useful theory or tool to treat engineering or practical problems. And since the physical chemistry or thermodynamics is general and useful to many branches of problems, they have high degree of generality. And high degree of generality actually means theory is quite abstract and quite often mathematical. Some students do not like physical chemistry or thermodynamics much because due to the abstractness or mathematics involved. However, being abstract or being mathematical is necessary to have a high degree of generality, and which is actually necessary to treat a wide variety of engineering and practical problems. And thermodynamics is a theory for aggregates of molecules and focusing on macroscopic properties like dissolution, mixing, phase, or its separations or its change. And if you want to go to molecular level, one needs statistical mechanics. So this is a kind of advanced course beyond thermodynamics. So, okay, now let's go to more, let's focus on thermodynamics. Very important concept in thermodynamics is equilibrium. And there are two kinds of equilibrium called mechanical equilibrium and thermal equilibrium. Mechanical equilibrium is well connected to the concept of pressure. I think everybody knows the concept of pressure. You have a force here, and you have area here, pressure is force divided by area. So quite simple. And this pressure is connected to mechanical equilibrium due to the following reasons. Okay, we have two boxes here. This is one here, the second one is here. And they have wall separating those two boxes. And this wall is movable. Let's make it movable. Then, if the pressure in box 1 is larger than the pressure in box 2, wall moves to the right. If the pressure in box 2 is larger than the pressure in box 1, wall moves to the opposite direction, to the left. And water doesn't move when two pressures, P1 and P2, are equal to each other. And this is called mechanical problem. Why it is called mechanical? This is coming from force. Force is a key concept of mechanics. Therefore, since this P, pressure, is related to force, we use a term mechanical. And at mechanical equilibrium, the boundary or wall between the two regions doesn't move. Therefore, there is no work between the two. Neither of them pushes the partner. In the thermal equilibrium, this is connected to the concept of heat. Let's have a wall here. This is now heater transferable. Heater can be transferred through the wall. And at this point, I want to introduce one term called adiabatic. Adiabatic wall means through that wall, there's no flow of thermal energy. And this thermal energy is roughly equal to heat. So essentially, heat means the flow. Actually, heat means flow of thermal energy. So heat transferable wall means a wall through which thermal energy can be flowed. And at this point, important quantity is temperature. This is like pressure in the previous slide. So if the temperature in a box 1 is larger than box 2, then thermal energy flows to the right through the boundary. Boundary doesn't have to move, but still energy goes from left to right. And thermal energy means there's no flow of energy, and at this point, temperature between the first box and second box are equal. So what is temperature? Temperature is a quantity to describe the direction of the flow of the thermal energy. And at this point, we note zero law of thermodynamics. In the next later, I would say something. I would say first law and the second law of thermodynamics. But before the first and second, we have a zero law of thermodynamics. This means, this actually states, if the thermal energy flows from A to B and from B to A, it can flow A to B. What I mean here is, I have A here, I have B here, I have C here. If heat goes from A to B, and if heat can go from B to A, then it can go from A to C. And this is actually quite important stuff, because if we write down the flow of thermal energy, as a kind of inequality, like A larger than B, B larger than C. This means thermal energy flows from A to B. Thermal energy flows from B to C. Then this actually leads to a result that thermal energy flows from A to C. And this kind of a relationship is called transitivity. And transitivity is a necessary condition that a process can be described by numbers. Everybody knows the concept of temperature, but temperature is a number, and the number called temperature can be assigned to the flow of thermal energy because transitivity is satisfied for the flow of thermal energy. The flow of thermodynamics states or assumes the transitivity of the flow of thermal energy. In other words, the flow of thermal energy declares or states that there exists a quantity to describe the flow, direction of the flow of the thermal energy. And the route of the flow, I mean, if the flow coming from A to B, A is usually called hot, B is usually called colder or cooler. So due to the transitivity, we can define a quantity which can describe the hotness or coldness of our system. And this quantity is called temperature. Therefore, the flow of thermodynamics states that there exists a quantity called temperature. So without this law, thermodynamics is impossible. Now, on the basis of this law, we can define temperature. And by defining temperature, we can specify the direction of the flow of the thermal energy. Now we have heat and the pressure, heat and work. Work is more easier when we come back to mechanical equilibrium. We have a force here, and this moves to some extent. Then work is F times delta X, right? So we have heat and work. That's what we introduced. Furthermore, if we have two boxes, they may exchange molecules or atoms and so forth, and they may cause matter. So at this point, we introduced a system can gain or lose or exchange heat, work, or matter. And at this point, we now focus on a part of the, we want to focus on one box, and that box is called system in thermodynamics. System is the body of matter of interest. And what is the rest? Out of the system is called surroundings. So at this point, we differentiate two boxes. Here in this figure, this box and this box are kind of treated on the same footing. But in thermodynamics, we treat it differently for the system and surroundings. System is the part you are interested in, and surroundings is not the part of what you are interested in. And system and surroundings can exchange heat, work, and matters. And in thermodynamics, there's a convention that heat is often written mathematically as dq, and the work is often written as dw. This d is actually means small amount. So essentially, this is in corresponding to the expression for differentiation. So this means small. And Q is usually means heat. W means work, as a abbreviation of the English word of work. And the convention in thermodynamics is that if system gets something, then that is assigned a positive sign. And if system provides something to the outside, that's given a minus sign. So in the case of heat, this dq is positive when system gets thermal energy from the surroundings. And in the case of work, dw is positive when system is given a work from surroundings. In other words, dw means a work done by surroundings to the system. So by changing the sign, work done by the system to the surroundings is minus dw. This is a convention of thermodynamics. And this minus dw is quite often used. And I will also use this later. Please do not confuse the work done by surroundings or done to surroundings. Done by surroundings, in this case, just dw. Done to surroundings is minus dw. And system is quite often something like an engine. And in the case of engine, people are concerned about the work done by the system to the surroundings. So people often use this minus dw as a work. Please do not confuse. And also, there are many types of systems. But there are quite well used 4 categories of systems. And system is categorized in terms of the exchange with the surroundings. Isolated system, no exchange of heat, work, and matter. So it is isolated. Adiabatic system, no exchange of heat. So work can be done, matter can be exchanged, but there's no heat exchange. This is called adiabatic. Closed system, in this case, heat and the work can be exchanged, but not for the matter. And open system, exchange of heat, work, and matter, or everything. For example, our body or any cell, if we treat our body as a system, it is an open system because we have heat and we move and do some work, and we get the oxygen and emit the carbon dioxide. We exchange heat, work, and matter. So our system is an open system. Our body is an open system. But since the treatment of an open system is most difficult, quite often we stick to closed system, which is easier to treat and easier to analyze. And in thermodynamics, we also study closed system first and move on to the open system. Now, as we define system and surroundings, we move on to first law of thermodynamics. I guess everybody knows this. First law of thermodynamics means mathematically this is very, very simple. du is equal to dq plus dw. du is a change in the internal energy. What is internal energy? We have system here. And the energy involved in this system is called internal energy. Why internal? It's internally in, because that energy is internally within the system. And this du, the change in the internal energy of the system, is equal to the heat transformed from surroundings to system, plus work done by the surroundings to the system. And please note that this, we have plus or addition here. Or if you change the convention of the work, it can be subtractions. But whatever it is, they are added or subtracted. So that means heat and work can have same unit. Same unit. And being same unit, they can be added or subtracted. So heat and work can be both provided as energies to the system. So internal energy, so dq or dw are both energies. And work and heat are therefore different forms of energies. And there are different forms of energies, even though they look different. For example, if you say work, you push something and make it move. If you say heat, you feel hot and you emit your hotness to outside. So heat and work look quite different, but in fact, they are both energies which can be added or subtracted together. So this is one discovery in the history of thermodynamics. Although they look different, heat and work are both energies, essentially same thing in the different forms. And another point of first law of thermodynamics is the internal energy U is a state function. The concept of state function is very important in thermodynamics, and it's the key to the development. We will see it in the introduction of second law of thermodynamics. And state function means its change are determined only by the initial and the final states of a process without regard to the path of the change. And if a quantity is not a state function, it is called path function. And heat and work are both path functions. And actually, path functions are not convenient. Initial state, you have if you have an initial state here, and you have final state here, and to know the work or heat provided in the change from this initial state to final state, you have to know the intermediate paths too. If the path is different, work and heat is different. So one has to know all the histories to know heat or work or any path functions. So this is not really convenient. For example, in here, in this lecture, we have about 100 people. We can count the number of people here. And this number is a kind of state function because we can quantify the number of people here just by counting the number at this point. We do not have to count Well, we don't have to know how many are there in this Zoom session 10 minutes ago or 100 minutes ago or so forth. If the number of people is a half function, you have to know what happened 10 minutes ago, or what happened 5 minutes ago. And this is not convenient. So our convenient quantities are quite often state function. And history of thermodynamics is very much nearly equal to pursuing state functions. So, great discovery of first law of thermodynamics is actually that internal energy is a state function. So mathematics is very simple. du is equal to dq plus dw. But what is involved or what is behind is not something which can be seen from this equation. That is, u is a state function, but q and w is not. And in an isolated system, there's no heat exchange and there's no work exchange. Therefore, dq and dw are both zero. So u is constant. And please note the conventions of sign. And plus for systems gain or take. Now, we are focusing on the change or process. And at this point, there's a important concept called reversible process. Okay, before that, we say equilibrium. This is thermal equilibrium and mechanical equilibrium. Thermal equilibrium is attained by same temperature. And the mechanical equilibrium is attained by the same pressure. Hold on, let's see the chart. And the reversible process okay. It's to you. Okay, and the reversible process means process is kept at equilibrium, and this is not really possible if you think it. You know, for example, you have pressure here. This is a system pressure. And this is a pressure from surroundings. And just say pressure of the surroundings will be called PEX. EX means external. First two letters of external. And at equilibrium, P and P is equal to PEX. So no move, there's no move there. But process is a kind of a change or motion. So at equilibrium, no change is possible. So in other words, reversible process are kind of contradictory term. It's not really a contradiction, but it sounds contradictory. Then what is it? You have P here, system pressure. You have PEX as a pressure from surroundings. If P is larger than PX by very, very small amount, wall moves to the right. If P is smaller than the external pressure by very, very small amount, wall moves to the left. And the reversible process or equilibrium process is a kind of limiting concept in which epsilon goes to zero. So if epsilon is very small, motion is very, 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 very small. If epsilon is very small and negative, motion of the wall to the left is also very, very, very small. So reversible process is often called quasi-static process. Quasi means almost or kind of, a bit difficult word. And static means no motion. So no motion process is a kind of contradiction, but almost no motion process and almost no motion. Then how slow it should be? It can be arbitrary, like represented by this epsilon, but this epsilon must be very, very small. And the limit of this epsilon goes to 0 is called a reversible process. Therefore, if one has real reversible process, then the process takes infinite amount of time to make the change you want. So in that sense, this is a kind of ideal concept. But this is quite useful. And reversible process, outside pressure is equal to the system pressure. And here we note work. Work is actually given by Pex dw. And where does this come from? Okay, suppose this is area is A, and the length of L, then V is equal to L, and when area is fixed, then dV is equal to A dl. Therefore, work done by surroundings is equal to force times dl, and the force is A times Pex. Therefore, total force minus dl, which means minus Pex dv. And the point is, work is defined by the work. Work is defined as the one done by surroundings. Therefore, we have to use Pex instead of the system pressure. So this is an important point. So if we say dw or d work is equal to minus Pex dw, this pressure here is not a system pressure, and this is equal to the pressure of the system only for the reversible process in which Px is P. So please note, work and also heat too are measured with references to surroundings, not a system. This is actually the concept of thermodynamics. In thermodynamics, we measure something by looking at or referencing the surroundings. Okay, when we say the work, now let's focus on the process which happens spontaneously. You leave it and it happens. That's spontaneous. And we have a concept of maximum work here. Again, we have a system here, and which has a pressure of P, and the surroundings, which has a pressure of Pex. Now let's think about spontaneous process. Spontaneous change, a change which happens without doing anything from outside. Then let's say how volume change dV in the spontaneous process. dB is positive. That means expansion. Expansion happens the system pressure is larger than outside surrounding pressure, outside pressure. If dB is negative, that's contractions of the system. And the contraction happens, external pressure is larger than system pressure. So we have two conditions. And when we want to make a theory, two equations or two inequalities is less convenient than having a single equation or single inequalities. So like if one has to memorize things, it is easier to memorize a lesser number of things. Therefore, even though we have two conditions here, we want to make it into a single condition. Then the condition of spontaneity can be summarized as PdP is larger than PEXdB. This is because if dB equals 1, PEX. So just multiply TdV, we have this expression. And if dB is negative, the condition is P is smaller than PEX. Again, let's multiply dV. Then we again reach to arrive at this expression. Therefore, this is a single condition for spontaneous process. And since dW is minus PEX dW, let's add minus sign here, which means, so by doing so, you have a different direction with inequalities. Then we want to make this expression more connect to the concept of work. Okay, let's have in a reversible process, PEX is P. Therefore, the work in a reversible process is dW is minus PdW. And this the REV means reversible for three letters. And in the general case, dW is equal to minus P EX dW. Therefore, this single condition of spontaneity can be rephrased in terms of the work as D reversible is smaller than the work in general. And in this case, in this general case, PEX is not assumed. So this is a general case. So the condition of spontaneous process leads to this condition for work. And in thermodynamics, it is conventional to write this equation in this inequality in terms of the this written. This inequality is conventionally written in thermodynamics with a minus sign here. So dW, as I mentioned, the work done by the system. So this is called maximum work. And this maximum work is the work done by the system. So this is a bit point of confusion. Without minus sign, the condition of spontaneous process is given by dW is larger than dW reversible. So this is so with this condition, we have to say the inequality as minimum work done to the system. by surroundings. This, but in thermodynamics, there's a convention that we had minus here. So this is called the principle of maximum work. And this maximum work actually means the work done by the system to the surroundings. So we now have a condition for the spontaneous process. So this is actually provides a law for change. Law for the change. If dW, this minus dW is larger than minus dW reversible, then this does not happen. Such a change is not spontaneous. If you leave it a system like that without doing anything, such a process would never happen. So this is a condition for the law of the change. And in equality, this is a limit of the change. So this is a limit. Beyond this limit, no such a change is possible. And up to this limit, work done by the system becomes the maximum. So this also poses a limitation for the spontaneous change or spontaneous process. Now we are working on work. So we say the direction and limitation of a process is given by this expression, the principle of a maximum work. However, work dW depends on the path of the process. Work is a path function. And the path function, what I mean here. Okay, let's say this is, I said, no, this is not P, this is PEX. So this, we have PEX here. And then how the work is given is the work is determined by the integration of this curve. Okay, suppose minus dW is minus PEX and dV. And this is the initial point, and this is a final point. But if we have different paths with the same initial and final points, then since then due to this expression for the work, the total work done in this black path is this area. However, the work done by this blue path is the area of this blue part. So evidently they are different. So work done by system is given by the area under the curve, and this area depends on the path. So work is a path function, it's not a state function. So this is not convenient. You have to know the process or the intermediate stage of the process. So this is not convenient. So at this point, also want to remind you that the concept of the mathematical concept of the exact differential. Exact differential is related to a concept of state function. Any expression dq is called exact differential if their integral over one path is the same as another integral over the different path with the same initial and final conditions or initial and final states. So Q is a state function. That means independence from the path, and the value is determined by the present state. Then if it's a state function, its small change dq is the exact functional. So if a function is a state function, it is convenient since information about the path is not necessary. So path function is not convenient to express a law of physics or chemistry. One has to seek for any state function which can be useful to express this condition of spontaneous process. Okay, now let's think about the spontaneous process in terms of heat. So we say first law of thermodynamics is called du is equal to dq plus dw, and the internal energy of the system is a state function, as I mentioned repeatedly. And when the initial and the final states are the same, du is the same too. Now I have a initial state here, I have a final state here. One can have many some arbitrary path. However, let's pick a reversible path here. Reversible path here. And since du is a state function, the value of du does not depend on the path. Therefore, du in a reversible process is equal to du over other paths. By using this, let's change. Let's derive another expression for the direction of a spontaneous process. Okay, we had this. The minus dw is smaller than minus dw reversible, and this is the same as dw minus dw reversible is positive. And however, du is equal to du plus dw, and this is equal to dw reversible. And in this reversible path, one may have heat and one may have work too. And the heat exchange in the reversible path is called dq reversible, and the work done to the system by the surroundings are called dw reversible. So du reversible is equal to dq reversible and dw reversible. Therefore, dq reversible minus dq is equal to dw minus dw reversible. So the condition of spontaneity, condition for the spontaneity of a process is relating in terms of heat as dq is larger than dq reversible is larger than dq. This expression means heat received by the system from the surroundings is maximum in a reversible process. But of course, dq is not the exact function. dq is not the exact differential, or it can be called dq is an inexact differential. In other words, heat is a path function. So this expression is not still convenient. However, for the work, there are many types. Many types. Like, as I mentioned, pressure, volume. However, another kind of work is surface tension times area Another type of work is charge, electric charge times potential, electrostatic potential. So there are many works. However, for the heat, there is only a single type. Therefore, we have only single expression. So this a bit more convenient. Then we now have entropy. Why entropy is introduced? Because it is a state function. Then how it is defined? We have dq is smaller than dq reversible. And now I put equality here. This equality means a reversible process. And inequality, irreversible process. And since this happens, it is simple to see inequality is the same by dividing by the temperature T. And this integral was proven to be so this differentiation was proven to be exact differential. Exact differential. In other words, this integral defines a quantity S, which is a state function. And this S is called entropy. So actually, the definition of entropy is a bit involved. To define entropy or entropy change, let's say, to define entropy or entropy change between initial and the final points, you have to first find a reversible path. Even though your real path or actual path is something like this black line, you first set aside this actual path, and you have to find this reversible path. And by looking at this reversible path, you compute dq or dq reversible. And by dividing by dq reversible and add them up, that's entropy or entropy change. So therefore, the definition is a bit involved. Entropy or change is introduced by referring to a reversible path. But what has been proved in the history of thermodynamics is a change in the entropy S does not depend on the choice of the reversible path. Therefore, entropy is a state function. At this point, one has to note T is the temperature of the surroundings, not the system. And what is important is this dq, so S, ds, S, entropy S is a state function. So, and here, now here comes the second law of thermodynamics, is quite well known. Without exchange of heat, dq is 0, ds is positive or 0. So S is a state function, and as far as heat exchange does not exist, the direction of change is determined by or described by the change in the state function S. You don't have to see how the process go through the intermediate states. So you don't have to know it. All you have to know is the initial and the final states. And once you know how to compute the entropy at the initial and the final states, you can know the process to the initial to the final states can happen spontaneously or not, as far as there's no exchange of heat. Therefore, this is quite convenient because one has to know the intermediate states. And S is provided by this expression as a difference. So one has to fix the 0 point or origin of the entropy. And that's fixed by third law. So as I mentioned, why entropy is involved? Because heat, also work, is inconvenient to build a theory since it is not a state function. It is a path function. So it is desirable to introduce a state function which is related to heat. Then the theory is much easier to be operated. This is the reason why one introduced entropy. Then where does it go for about work or heat? Still, for example, work is the actual work, the actual stuff the system does to the outside or surroundings. Therefore, this is still useful. Therefore, people still use it. So from the viewpoint of practical applications, work is still quite important. Still, one wants to know a state function. One wants to have a state function which is related to heat. Therefore, entropy is introduced. So when you see this expression, the computation of entropy is quite involved. And therefore, the meaning of entropy is not very, very clear compared to, for example, to internal energy or work. So meaning of heat or entropy, sorry, this is not really heat, sorry, this is entropy. So meaning of entropy will be disclosed at the molecular level with statistical mechanics, which is a kind of advanced topic beyond thermodynamics. So we can now have spontaneous, we can have a condition, or we can kind of summarize the concept condition of spontaneous process in terms of entropy. Condition of spontaneity is provided by this, and divide the both sides by temperature. Then at least the left-hand side becomes state function. And inequality is a reversible part. And if it's inequality, this is an irreversible part. So we have a first law of thermodynamics here. And the first law of thermodynamics is valid both in the reversible and the irreversible process. So by using reversible path, dW is equal to dQ plus dW, and which is equal to dQ reversible plus dW reversible. And by dQ, the dQ reversible is equal to TdS by definition. So the concept of maximum work can be rephrased as TdS is larger than the heat actually absorbed. So this is the heat actually absorbed. And TdS, this is computed as a state function. So if so if one knows where you are for the final and initial state, then just by knowing the change in the entropy between those two, you can predict the amount of heat which can be absorbed to the maximum. So this is quite useful. But still, this expression have dq. This is a path function. So expression is not free convenient yet. Therefore, let's move on more. Now, we want to reduce the generality of the discussion a bit. Okay, so suppose work, just for simplicity, suppose that work is only of PV. So dW is always minus PV. And another condition is let the temperature be kept constant. By imposing these conditions, in other words, by reducing the generality of the discussion, we can have a state function which can describe a spontaneous process. Okay, so let's have a condition of spontaneity at constant volume. First law of statistics, first law of thermodynamics, du is equal to dq reversible plus dw reversible, and dq reversible is equal to TdS. And also as a first law of thermodynamics, du is equal to dq plus dw. And TdS is larger than dq. Therefore, we can change the expression. Okay, since volume is a constant, dV is equal to 0. Therefore, dW is 0. So 0 is dW, and since ds is larger than dq, this dW must be larger than dW reversible, right? TdS plus d reversible is equal to dq plus dW. And this TdS is larger than dq, therefore dW must be larger than dq reversible. And the dW reversible is equal to du minus tdq reversible, and this is equal to du minus TdS. And since temperature is constant, T can be introduced into the change D. What I mean is TS is TdS, since this T is constant. T is constant. Now, du minus dTs. Therefore, du minus Ts. And u minus this Ts is called thermohonic energy or thermohonic free energy. And one has to note, A is a set function since u and T and S are so. So spontaneous process at constant volume and constant pressure is given by dA is negative or is equal to 0. And this inequality, not inequality, equal, in the case of equal. Reversible case is equal, therefore reversible case is equal, so reversible case is equal. And in the case of reversible case, the system is in equilibrium with the surroundings. So equilibrium at the constant temperature and volume is given by dA is equal to 0. And this is a very convenient expression because as far as temperature and the volumes are constant, the direction of the change, limitation of the change, direction of the spontaneous change, and the direction limitation of the spontaneous change is expressed by a change in the state function called thermodynamic energy. So once you know the initial state and the final state, and you don't have to know which path you take. As far as temperature and the volume is constant, you can know in advance without knowing the path whether this change from I to F can happen or not. Now let's move on to Gibbs free energy. In this case, instead of volume, we keep the pressure constant, and we still stick to the condition that work is given by only about PV. So dW is still minus PEX plus dW. So, okay, now temperature and pressure are kept constant. And actually in thermodynamics, this means constant temperature or constant pressure means thermal equilibrium is attained with the surroundings, and the mechanical equilibrium is attained with the surroundings. This is actually the meanings of constant temperature and constant pressure. So thermal equilibrium means T is equal to external temperature of the surroundings. Mechanical equilibrium means system pressure is equal to the external pressure. Therefore, constant pressure means dW is equal to minus PEX dB is further equal to P system pressure times dV. So this makes the problem a bit simple. So condition of spontaneity at constant T and P. Okay, this is the first condition. TdS is equal to or larger than dQ. And we have dW is now equal to minus PVW, minus PdW. And principle of maximum maximum work means that this dW is larger than dW reversible, and which is equal to du minus TdS. Where does this come from? It's here, or it's here. dW reversible is equal to du minus TdS. And the dW minus TdS, again, T is constant, therefore T goes inside of this D, change D. Therefore, D in parentheses, you have U minus TS. And now we use this and this. I'm sorry, so not this one, this. Minus PdB is larger than du minus TdS. And P is also constant, so this is equal to minus dPV. Therefore, du minus TS plus PV is negative or 0. So this one, U minus TS plus PV is called Gibbs energy or Gibbs free energy. And an important point is G is a state function since U, T, S, P, V are also. So we can now arrive at the condition of spontaneous process, condition of the spontaneity of the process at constant temperature and pressure, which is simple. G decreases. And at equilibrium, at the constant temperature and pressure, G does not change anymore. So now we arrive at the condition of a spontaneous process at constant temperature and pressure, which is expressed only by a state function. So in thermodynamics, I think everywhere in the world, we teach Helmholtz free energy and the Gibbs free energy because we want conditions of, we want the conditions of spontaneity of the process that are expressed only by a state function. Okay, now we want to bit generalize our point. Okay, now Helmholtz energy. Let's stick to again the Helmholtz free energy. Now temperature is kept constant, but we do not have any restrictions to the type of the work. What I mean is dW is equal to the PV work plus non-PV work, like for example, electricity or surface tension or so forth. So at the constant volume, this term is 0. So dW is simply equals to dW non-PV, and this is equal to the dW reversible. And as I mentioned over here, as I mentioned over here, dW reversible is equal to du minus TdS. That again comes here, and this is dA because T is constant. So we have dA is smaller than dW non-PV. This is a condition for the spontaneous this is a condition for a spontaneous process. This is an inequality for the work done to the system because there's no minus sign here. There's no minus sign in front of this dW non-PV. Therefore, in order to express, in order to have a different expression in terms of work done by the system, minus dW non-PV is smaller or equal to minus dA. So this dA is the maximum work done by the system. This expression shows maximum work done at the constant temperature and the volume is given by the change in the thermal free energy. If one has, so suppose you have a I final and whatever path you have, once you know what is initial and final states, then just by computing the change in the delta A, you can have the maximum work which can be possible by the system. So this it provides a limit for the work you can do, what the maximum the system can do. In the case of Gibbs case, story is the same. Temperature is constant and pressure is also the constant. So we have PV work here and non-PV work here. This is the same expression as the one over here. And at this point, at constant pressure, PEX is equal to P. Therefore, dW is equal to minus PV plus dW non-PV. And this is larger than dW reversible, which is du minus TdS. Therefore, this PdV is here, du TdS here, and the minus, since minus PdV is equal to minus dPV, because P is constant, you have d in parentheses, du minus TS plus PV is smaller or equal to dW non-PV. This is an inequality for the work done to the system from surroundings. In order to express the work in terms of one done by the system, minus dW non-PV is smaller or equal to minus dG. So this is the maximum work done by the system. Maximum work at the constant temperature and the pressure is given by the change in the Gibbs free energy. So this is also, again, a very convenient expression. So we can summarize those stuff. So suppose now the work is only about PV again. So du is equal to dq plus dw. So this is the first law, and this is valid in any process, including both reversible and irreversible processes. And let's pick up a reversible process, tq reversible plus dw reversible. And since this is a reversible process, this is equal to TdS by the definition of the entropy. And since this is dW reversible, in this case, PEX dB, however, this PEX is just P. Therefore, this becomes a PEX. So we have a du is equal to TdS minus PdV. This is called fundamental thermodynamic relationship, which should be known to everybody who learns thermodynamics. But we have to know that this is an expression only in terms of state functions. So this is quite convenient. And if internal energy U is expressed only as a function of S and V, we have this and this. So by the law of partial differentiations, this T is provided by du over ds at fixing the volume. And P over here is minus du divided by dv by fixing ds. And actually, if you want, and actually one wants to know du over dt temperature by fixing volume, however, the expression is more involved. So this is not really, this is a simple equation. However, so entropy, so this is a simple expression, what means this partial differentiation is quite simple by taking entropy and volume as independent variables for T. However, entropy is not an easy quantity. Measuring it is not easy to measure entropy. Temperature is much easier. So one wants to have temperature as an independent variable. So for this purpose, thermal free energy is more convenient. This is a definition. A is equal to U minus TdS. So dA is du minus TdS minus SdT. And when this du expression is written here, one arrives here. I think this is known to everybody. So if A is expressed as a function of temperature and volume, one has a simple expression. And S entropy can be computed by the temperature derivative of A at the constant volume. In the partial differentiation, one has to note what variables are fixed. And for the pressure, volume derivative of A at constant temperature is the pressure. So Helmholtz energy is convenient when temperature T and volume V are taken to be independent variables. Then what happens in Gibbs case? I think this is quite, I'm simply rephrasing what's written in the textbook. Gibbs free energy is given by U minus Ts plus Tb. So just by taking the differential, du plus Vdp plus Pdb Tds Sdt. And just by using du is Tds minus Tdb, we arrive at minus Sdt plus Vdp. So when G is expressed as a function of temperature and pressure, you have a simple expression. Entropy is given by the temperature derivative of Gibbs free energy at constant pressure, not the volume. And the volume is given by the pressure derivative of Gibbs free energy at constant temperature. So Gibbs energy G is convenient when the temperature T and the pressure P are taken as independent variables. And this quite often correspond to experiments. So this is the final slide for today's lecture. Here I write, up to this point, I write spontaneous process. Spontaneous process. dg negative. And now I write the expression, I think, which is known to many of you. dg is equal to minus SdT plus dV. This dg and this dg, are they same? No, they are not the same. So here we have two meanings of the same expression dz. Condition of a spontaneous process is decreasing dz. dz is negative or equal. And this, as I mentioned, or as showing the derivation over here, this comes from dq reversible is larger than dq. And this is the process. So change with time. Process is a change over time. So this is a condition for spontaneous process at the constant temperature and pressure. And the equality is at equilibrium. So, but this, as I mentioned, this is a process. This is a condition for a process. Process means change almost. So actual meaning of this dg is negative is this. G is actually a function of T, P, and others. Like in the chemical reactions, concentrations of reactants and products. And during the chemical reactions, until the concentrations of reactants and products change with time until equilibrium is attained. So this C, let's take it as a concentrations in chemical reactions. So these are variables other than T and P, and T is the time. And since temperature and pressure are constant, that means T and P do not depend on T. Actual meaning of dg is negative means G decreases with time at constant temperature and pressure. Variation of G with T is non-positive with temperature and pressure kept constant. This is the meaning of this dg is negative or is equal to 0. And when equilibrium is reached, then there's no more change for G against T. So this is dg is equal to 0 involved in this expression. If I say dg is negative or equal to 0, this equality is here, and actually this means this. dg at temperature, time dependence of G is now 0 at constant temperature pressure. And if this is G, then this Ct is now does not depend on T anymore. T does not depend on T anymore. C does not depend on T anymore. What I mean is at equilibrium, the concentrations of reactants and products are constant or constant against time. So she does not depend on T anymore. And now she is function only of T and P. Therefore, G, which was a function of T and P and C, but since C is a function of T and P, now G is a function of T and P. Then when expressed in this way, G at equilibrium. So at this case, here, G, dg over G d time is implicitly implied. So G at equilibrium as a function of T, P, and P, in this strict condition, dg is equal to minus SdP plus dP holds. And same arguments for Helmholtz too. So please note, dg have two meanings. One is the condition of spontaneous change, and this actually means dg over dt, change against time. And when this becomes 0, which is at equilibrium, now G is a function only of T and P. And in this condition, dg is equal to minus SdT plus dVdP. Please do not confuse two meanings of dg. Okay, so for today's talk, this is it. So 3 weeks later, we would focus on the chemical potential and its applications. Okay, thank you. So I will stay here on this Zoom. So if you have any questions or any talks, let's do it.
Okay, thank you very much, Professor Matsubayashi. That was a really nice talk, and it is also new for me to learn from you that there is another path to arrive to such an equation. So yeah, I just want to formally open the Q&A session, the discussion session. So if any of you have a question, so please raise your hand, or just I wonder if you can open your mic and deliver your questions. Okay, so please. Meanwhile, I will look at the YouTube channel if there's a certain something happened there. Excuse me. Okay, so any of you have a question? Okay, I also forgot to to mention that this kind of collaborative class we have started since I think 4 or 5 years ago. So every year we the Brawijaya University organize this kind of a collaborative class with various uh, professor and also industrial expert from around the globe. But usually in normal situation we have the professor, the expert to come to our university to physically give a lecture in the class. Except that yeah, in this unfortunate time that we cannot have anyone in the class. Even I myself, I cannot physically give a class now for that. Okay, so is there any of you have a certain question? So Sensei, I'm just wondering that just a small comment. In our case, in our work with the battery, so theoretically, if we know the initial and the final state of a battery, that means we can argue the maximum work that can be done by the battery. But like we can set that's the maximum work that you can do with this battery, and in actually you can only have lower than this.
Yeah,
Because,
actually, that's a point. Actually, that's a point. Quite often, this expression is used in the field of batteries. So by looking at chemical reactions and by knowing the reactant and the products, one can know this dg or minus dg. And the battery work is a kind of battery work is a one of a non-PV work. So by knowing the chemical reaction on the battery, one can predict the maximum work, which is actually maximum voltage that can be attained by the battery.
I see. Okay, so and I also I understand that we are very careful about defining which one is the which variable belong to the surrounding and which variable belong to a system. Well, for example, you emphasize that the pressure in the work has to be written as an external pressure, and one thing that really make me curious is about the definition of the entropy itself, because you see the definition of the change of the entropy is equal to the change of heat in reversible process divided by the temperature, and you emphasize that this temperature is belong to the surrounding. However, yes. The numerator itself requires that the heat is coming from the reversible process. And in reversible process, the temperature has to be equal to the surrounding. So I wonder if this is really relevant in this situation, because the numerator has to be reversible, so the temperature itself has to be the same.
Oh yeah, you're right. You are right. So in this case, this T is a system temperature because it's a reversible. You are right. You are right. But this T is outside temperature. So yeah, you're right. So this is TX, but this, you're right. You're right.
Yeah, I mean, but I somehow I can understand, because this traditionally this definition is coming from the Carnot cycle.
Yeah.
The Carnot cycle is working with two different temperatures from the reservoir. So it is an external temperature.
Yes,
so speaking, but yeah, in this sense, I can understand that. Yeah, and yesterday I just I actually got a responsibility to arrange for a electronic device set up for a hybrid class. So we can have an offline class, and at the same time we will have an online class. So yeah, yesterday I was preparing for that and doing some tests, and it just happened that I invited a student from thermodynamics class to test that kind of device. Maybe I will share the traditional setup in our class. So it's a very interesting one.
Yeah. So I for example, in particular for DG, the meaning of DG, I take kind of non-traditional way of talking.
And Puan, are you there, Puan? Puan Maharani?
Oh yes, sir.
Okay. She has a yesterday. She has a question that I think it is very interesting. So if you have if you can repeat the question to Professor Matsuhayashi.
Yeah.
Okay, sir, I have a question. We know that open systems are characteristic by the exchange of heat, work, and matter, while the equilibrium has the same temperature and pressure characteristic between the system and the surroundings. Can open system be in equilibrium? And can the open system be in a reversible process? And I have many questions about the Gibbs concept. Do this Gibbs concept and formulas apply to all systems or only to closed system? How is this Gibbs concept when the system is open? Thank you, sir.
Yeah. Okay. In that case, yeah, that's a thing about 3 weeks later. But in the open system, one has to introduce the concept of chemical potential. So somehow the condition of spontaneity is relating using chemical potential. Do you answer your question?
A little bit abstract, I think. One. Yeah. So basically, Professor Matsubayashi Sensei said that in order to explain the condition for the open system, we have to introduce a quantity called the chemical potential, and that will be discussed on the 3 weeks later on the meeting 3 weeks later. Yeah, I think probably it's not quite easy to discuss about the open system. However, I think Sensei, in your last slide, you shows that there's the spontaneous criteria. The condition for the spontaneous process is for the DG, the change of the Gibbs free energy for the PV work only. I think it's less than 0, has to be negative. Is this condition also apply for the open system?
Yes.
This also apply in the open
system. Yeah, applies to open system too. Yes.
I see. Okay, so because when we discuss about this kind of topic, sometimes we get confused with the limitation that we impose to the system. For example, we implicitly say that this is like one component or one phase system. Is it closed? Is it adiabatic? Is it working with so something like that, I think.
Yeah. So negative DG is negative. The condition of negative DG applies at constant temperature and pressure, and so this applies also to open system. Actually, to be more exact, we have to say it is considered to be applied to open system. It's considered to be valid at open systems.
Considered.
What I mean is, we do not have this. We do not have this kind of simple-minded proof for open systems. So the story is when we adapt the concept, when we adapt the condition of negative dg, everything is consistent. Therefore, we believe it.
Okay. I think that answer some of her question, but her first question. I'm sorry, Puan. Can you repeat your first question about the equilibrium? Open system can reach. Hello, Puan. You are there?
Yes, sir.
Yeah.
I mean, can the open system be in equilibrium? Because we know that open system are characterized by the exchange of heat, work, and matter. While the equilibrium has the same temperature and pressure characteristic. I mean, exchange of heat. It's temperature.
Okay. So what she asked is because open system allow for the material, for the heat, for the at least heat and material to be exchanged, can open system actually reach equilibrium?
No, I see. For example, okay, first to be kind of abstract, this is system, and this is surroundings, and you have something, and this is something too. And okay, these are things about 2 weeks later. This is a chemical potential here. This is a chemical potential in the surroundings. If the chemical potentials are equal to each other, there's no net exchange of this material. So equilibrium can be attained. And this can be written as this. Suppose you have a chemical reaction between A and B. So A has its own chemical potential, B has its own chemical potential. And as far as mu A is larger than mu B, A reacts into B. So at equilibrium, they become equal. So this is more like a temperature or pressure. I mean, the story is quite parallel to potential or temperature or pressure. So there is equilibrium in open system.
Okay. One, I think that answered your question, right?
Yes, sir. Thank you.
Okay, thank you.
Thank you. Okay. So do we have another question from the other students, perhaps? Does anyone want to have a question? There's one of student. Okay, so please, Dirga.
Okay. Thank you. まずはどうもありがとう to Professor Matsubayashi-san for your explanation. So my question is there any limitation when we do a thermodynamics approach in microscopic and when we do calculation in macroscopic?
Okay.
Is there any adjustment or something like that? Thank you.
Okay. This is a very actually deep question. We say macroscopic, but we don't know. We usually do not know how big a system should be to be macroscopic. Like molecule, single molecule or 100 molecules, that's probably not 100. Sorry, single molecule or 5 molecules, probably that is microscopic. And 1 millimeter, that's probably macroscopic. How about micrometer? In the case of micrometer, it can be macroscopic. Now, how about 10 nanometers? It's bit. It depends. So the boundary between microscopic and macroscopic is not clear, and not only clear, it's impossible to explain. The reason is there's no clear-cut explanation at the moment. Any textbook says, and any textbook does not say any nothing clear, essentially. So I'm sorry to say there's no answer to your question. So when you come to some tens of nanometers, all I can say is just to be careful.
Okay, thank you. Thank you, sir.
I'm sorry. Okay, thank you very much. So yes, so basically we have no clear definition on what is macroscopic and what is microscopic at this moment. Yes, and but as you said, there is a certain range that we have to be careful when we deal with that. Okay, thank you very much for the question. And now that makes me want to ask about the statistical mechanics. I wonder if in Osaka University in the chemical engineering department, do you have like a thermodynamics? I'm sorry, the mechanical statistic subject offered in the course for undergraduate?
Yes. I
see. Is it compulsory or is it elective?
It is elective, but yeah, it is elective. Yes.
I see.
No, thermodynamics is compulsory, but yeah, StatMech is elective.
Okay. So okay. Okay, thank you very much.
It's because statistical mechanics is not often taught in a department of chemical engineering. So our university wants to make a kind of challenge. And since this is a challenge, and we cannot make the statistical mechanics course compulsory.
Okay. But somehow I think your chemical engineering department is somehow different because you have a compulsory course in quantum chemistry, right?
Yes.
Usually, chemical engineering department doesn't have that quantum chemistry. I think it belongs to the science.
Yeah, the reason is we want to make. Actually, our department wants to make chemical engineering a kind of a molecule-based engineering of chemistry.
I see.
Therefore, quantum chemistry becomes compulsory.
I see.
And statistical mechanics was introduced several years ago as an elective lecture.
I see. So yeah. So as you can see, in this in the department of chemistry, in here we have every year we accept about 4 parallel class. Each class has about 50 around 50 students. So that's why today's lecture we have whole class come together. So we have around about almost close to 200 participants. Yeah. Okay. So is there any question from any of you? I think we already reached the time. So now it's we start about 5 minutes late, but now the time has shown to be 3 o'clock in Indonesia and 5 o'clock in Japan. So I think I'll give 1 minute chance for anyone who wants to ask questions. Let me see. And oh, there's one. Okay, Irwansha, a quick question. Okay.
Thank you. Mr. I'm wondering.
Okay.
I'm wondering about two meanings of DG.
Okay.
You mentioned that the time is non-positive, even though we know that time is non-positive.
No. This is not really a positive of time. This is a time derivative of G. You mean this one? This one, right?
In the variation of G with T is non-positive. T time is non-positive. And even though that we know that time is always positive, non-positive is mean negative.
Yeah, almost, yes. No. This here, I mean, yeah, T is okay. T is positive, and T always increases. And with the increase of T, G decreases. That's what this expression. That's what this expression means. So here, I say variation of G with T is non-positive. So here I implicitly say T is always increasing. Yeah, that's what is implicit here. T is always increases.
Okay. So interesting.
Okay.
So thank you. I'll explain in Indonesia. Jadi yang tadi Matsubaya Sensei bilang itu perubahannya yang tidak positif, perubahan J terhadap T. So what Professor Matsubaya Sensei implied is that the change of the Gibbs energy with time, that's the one that non-positive. Not the T, but the change, the variation. So it's the derivative is non-positive. But actually, Sensei, I think we can freely reverse the time flow in here, so we can have actually DT negative.
Yeah, so,
it's also not bad idea.
Yeah, but if we can reverse the time direction of time, G increases.
Because I think the time is symmetrical.
Yeah. But the key point of thermodynamics is time is not symmetric. Right?
Except that somehow I don't know, because you see we can have a negative pressure. We can have negative pressure. Somehow I have a sense that this thermodynamic equation is somehow need to be adjusted when we deal with the case of negative pressure. Somehow, because then negative pressure can force the chemical potential to become very, very negative, and Gibbs energy to become very, very negative, and we can get almost all systems to become very stable at a negative pressure. That's what I sense, but it's a long story. I think we can discuss it maybe in later time. Okay, so thank you very much. So I think the time has arrived that we have to end this session. So we are going to meet again with Professor Matsubayashi 3 weeks later on October 22. So thank you very much for Professor Matsubayashi for allocating your time in your effort for this collaborative class, and we are very grateful to have you here. So let us meet again 3 weeks later. Okay, and for all the students and also all the staff who have joined this meeting, I also would like to express my gratitude to all of you, and I hope that what Professor Matsubaya Sensei has delivered to all of us will become very beneficial to our understanding. Thank you very much. Okay.
Okay. Thank you. So see you in 3 weeks.
Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon.
Thank you, sir.
Okay, Sensei, I think the host would like to close the meeting, probably.
Okay. So,
Wait. I just remember. Is there any? Sorry, maybe I should done it 3 weeks later. I think.
I can stay in this room, this Zoom for some while.
No.
I can stay if we need to talk something.
No. Sorry, I just remember one thing, but it's already too late in my mind. I'm sorry.
Okay.
Okay, I'm sorry. Thank you very much anyway, and see you.
Okay, see you.
Thank you very much.
Well, thank you.